Thank you. And during the talk about these two data structures, we are going to cover a lot more topics like unfolds and comonads and writer monad and some other stuff. And I hope you will enjoy it. So, we'll start with a very simple scenario. In this scenario, we have some stream of persons, some people stream, which may be infinite. It's a stream. And we want to annotate the persons like, are there a sandwich? A sandwich means that if the age of the previous person is less than the current person and the next person's age is greater than the current person, then I want to just say this person is true. It's a sandwich person. Okay? I want to be able to create this val person with people with annotation. And there are several ways to do it. You may think about maybe a sliding iterator from the iterable stuff, but this is mutable, and in general, I try to avoid mutable stuff. Mutables are great in super low-level performance optimizations, but as a general rule, I try to avoid them. I think they are bad practice. The second option will be to just recurse using some pattern matching of the previous person, the current person's age, and the next person, which is not so nice. And the third option is to do some fold. Well, with fold, we can do everything, anything we want. We just fold over the stream. But we need to carry on the previous person's age, and we cannot compute on the current person because we need the next one, so we need to carry on both previous persons, and it will get very cumbersome and very, very ugly. So what can we do? It's not a usual operation. In usual operations over data structures like streams and lists, we work on the current element. There's no notion of context, of previous, of next elements. But here we need the previous and the next one. So zippers may help us here. So what is a zipper? A zipper data structure is, you can say, a regular data structure with both a cursor, a focus point, a current element, and a direction. There's always a notion in zipper regarding either left or right, up or down, next or previous, some kind of direction. Okay, a zipper is a combination with a directed data structure and a focal point, a focus, an element. Zippers can never be empty. We will talk about zipper for stream, which is a little bit straightforward and easy to see and implement. And the more complex scenario will be a zipper for tree. We'll get to it later. So let's start with a zipper for stream. Later we'll see why stream and not list, but for now a stream. So a zipper for stream, see, is a stream zipper. We have a focus element, it's in the middle. You see it. The focus, a concrete element. And we have a notion of lefts and rights, the elements that are previous and the elements that are the next elements, the rights. Regarding implementation details, how do I encode them? Well, the rights should be stream because they may be infinite. Okay, I don't want to use list or vector or some other strict data structure. So the rights will be a stream. And the lefts, these are open for implementation-specific details. We are holding the lefts as a reverse stream of the previous elements. It means that the head of the lefts is the previous element of the focus. It will help us with implementations. However, in most scenarios, we will get a cursor on a stream after we have already traversed the previous elements. So in that case, we should maybe think about using a vector, not a list. You will see later why. Don't use ever list here, or we can use vector, or in the general case, we'll use a stream because I can actually define a zipper starting with some element and a generator function that provides the previous elements and a generator function that provides the right elements. Okay? Can be infinite. Okay? This is what we've talked about. And we can use a vector maybe, but in a general case, a stream is better. Now, what operations can I get with a zipper? So here are some operations without the implementations regarding what can we do with it. So two very important operations is getting the next zipper, moving the cursor one place to the right. Okay? Why it's an option? Because we may have reached the end of the stream. Okay? It's an option. Again, with the previous, maybe we are at the starting element and we want to go left, we'll get a none. And index, we can delete the left element, delete the right element. Of course, it's immutable. You always get a new zipper. Nothing is mutable here. We can insert elements. We can do a lot of very mundane methods. And we have a toStream. Now, this is important. When I want to take my zipper and get the original stream, remember I stored the lefts as a reverse stream. I will need to reverse them, and then I will need to evaluate, traverse over the left element. So toStream in my implementation is a bit costly operation. Okay, we'll need to remember it because we'll see later why. Now, what about the classic monadic operations, the map, the flat map? Well, the map function is very easy to implement. We just need to map my function over the left side, map my function over the right side. Remember, if it streams, so nothing is actually evaluated, and also map it on the focus. What about flat map? Flat map is a very important operation in regular collections like list, like vector, like stream. Well, flat map is somewhat less useful with zippers. See why? We have the flat map, and now I need to flat map on the left side, and then just combine them into a zipper. And two things to note here. First of all is if for any element I get a zipper, meaning I'm getting something with a focus for each element, I cannot store all of these focuses. I lose them. I only store the focus of the current element that I'm on. So I lose some information here. Next, you see that on the left side and on the right side, I invoke the toStream. And when I invoke the toStream on the zippers there, I evaluate some part of them. So a flat map on a zipper is a very, very costly operation. And usually we don't do it. Actually, in many libraries implementation, third parties, you don't have a flat map. You'll see, you'll have something more interesting called co-flat map, but later. Okay, so flat map is less useful here, and actually not always provided. You can implement, of course, flat map if you want to. No need. Okay, before we'll go to the co-flat map and start talk about Comonads, let's talk about folds and unfolds. I hope you are all familiar with folds, either fold left or right on collections or fold on options. There will be fold on try, I think, in 2.12. Should be very good. So with a fold method, I can do anything I want with my context, with my data structure, or it may be even something which is not a data structure. We can collect, extract, compute, create anything. We can do anything. If I have to choose only one method on an option, I will choose fold and use it everywhere. Okay? Not saying that you should not use the other methods, but you can create any method you want on option, for example, using the fold. It's called a catamorphism in math. Kata, like going downwards. I'm taking my context, my option, my list, my try, my either, and then I create something out of it, an int, a string, an option, or something like that. Okay? And actually, before that, another example, you can create your own folds. What do I mean by that? Let's say that you have to design a game of chess, the business logic only. So you'll have something like a board class, which represents the current board. And you will want to be able to provide a move function, make move or something like that. And what it may return? It may return either a successful move and the next board or something like that. This is the first option, all went well. You may have specified an illegal move. You cannot encode everything in the type system. So for example, I make a move, but there was a check on the king. So I can do that move, or I move my knight over the board, or I move to a position which is already occupied. So illegal move may happen. So I can use a try, use an either, something like that. But I have another option. What happens if the move results in a game over? So just return the board with the game over. No, but if I return a regular board, I can still try and make another move. No, when the game is over, I want to ensure that the user will not be able to make a move even in compilation time. So I have 3 different types as a result. I have all went well, a board, an illegal move, some error message or something like that, and a game over state, something like finished board, game over board, or something like that. So let's return a type and call it move result. Here is a sealed, this is the important part, a sealed trait of move result. And we have 3 descendants, inheritance classes. Game continues, which encompasses a regular board. Illegal move, which encompasses the error message or what went wrong. And game over, which encompasses a finished board, which does not support the make move operation. And see, in the move result, here, in the trait itself, I provide only a fold method. And with it, I can do anything I want. You see, it's 3 callbacks, 3 functions, what to do on an illegal move, what to do on a game continues, something that will work with the board, and what to do on a game over, on finished game, something that will work on a finished board and will not be able to make another move. So is this a good fold, a bad fold? For example, in collections, in regular list, you have fold left, fold right, fold, reduce left, reduce right. You have a lot of folding op functions, and how can we choose the best one, the one that will support any operation that I want? So actually, there's a good fold detector. It's something that we can check logically, okay? And it's not proven or something like that, but if I can pass all of the possible constructors for the type that I'm folding off to the fold method, and if I will get the original object I started from, then I will consider this a good fold. I can do anything I want. Okay? For example, if I'm having an option, let's check the fold for option. Is it a good fold, a bad fold? So let's pass option has 2 constructors, none and sum. I will pass them fold none, fold sum dot apply, the constructor for sum, and then I should get the original object. And yes, this does not compile because the compiler will infer that the type of the fold is none, and I need to put the type parameter for the generics to be an option of something that I'm using here. But just to say that this is a good fold, okay? I can check it. For example, in our previous scenario, is my fold for move result a good fold? Let's see. Can I provide the on illegal move, the illegal move apply? Yes. Here, the game continues apply, and here, the game over apply. And I will get the original object I started with. So this is a good fold. Okay, I have now some mechanism to check my folds. It's not mathematically proven, but it's a nice intuition. And by the way, what do you think? Fold left, fold right on collections? With both I can do everything, but which of them actually adhere to this law, to this intuition, fold left or fold right? Fold right. If I will pass the 2 constructors for list, nil in the fold right, the first argument, and then the cons, the plus colon, I will get the original list I started with. So actually both fold left and fold right are appropriate, but fold right is according to this law, to this intuition. So why am I talking about folds? Can I fold over a zipper? Yes, of course, but more interesting is talking about unfold. What's an unfold? So if we said that folds are catamorphisms, the name in mathematics for unfolds is anamorphisms, ana for going upwards. So it's something that to create my context. It's very useful for a recursive data structure like lists, streams, trees, and we'll see example for stream and tree. And unfold, meaning I'm starting with a single value, an int, a string, a person, something like this, and I get a stream of ints or strings or persons or even something entirely else. By the way, there is no good rule of thumb, no good intuition regarding if my unfold method is perfect or not. If it can handle all of the cases, probably not. There's not too much information, starting with a single value. Here is an example, unfold for stream, starting with an element and getting a full stream. So let's take a look at the signature. Well, unfold, A is the values that I'm working with. It's not the result type. The result type is a stream of B's. Like with fold, if I'm having an option of string, I can fold it to an int. So unfold, I can start with an int and maybe get an option of string, or list, stream of strings. So A is the types that I work with, that I generate from, and B's are the results. So I'm starting with an element, the seed element, and I need to provide a function that from the element will return an option. Why an option? Because we need to stop when, we are generating a stream. It may be infinite, but we want to be able to express also finite streams. So we will stop once we reach a none. And for each element, we'll get an option of a tuple, of a pair of an output value, something to be put inside the stream of results, and the next element to work with. And we will just invoke f recursively. You see here? I will just invoke f on seed, get an option, use the fold on an option, meaning if I got a none, a stream empty, this will be the result. And if I'm getting a tuple, B and A, then I will just create a stream. The first element will be B, and then I will do a recursion, call and fold on the next element. Now, wait a minute. This looks like a recursion without a stop condition, with stop condition. No, there's the stop condition with the stream empty. But won't it cause some stack overflow or something like that? No. Because of the by name and lazy mechanics of stream, this will work quite nicely, and you can create infinite streams and work with them. And it's actually very nice. I've used it in some projects. For example, you have a workspace table in your database, and each workspace may point to the parent workspace. And I, from a single workspace, want to generate from a single workspace ID. I want to generate the path of workspaces up to the root, and then just use unfold with the generator function that will retrieve something from the DB. Yes, I know it's side effect, but for that project it was tolerable. And you just get the full chain, and it's very nice. So very useful, unfold for stream. We will later see unfold for trees. Now, why did I show unfold? What's the relationship with zipper? Because StreamZipper has a very interesting method called positions. Take a look at the signature. I'm a StreamZipper of A, and the method position will return a StreamZipper of a StreamZipper of A. Now, what's a StreamZipper of StreamZipper? Remember, a StreamZipper is actually like a stream with a cursor. So I'm having a stream with a cursor, but the elements are themselves streams with cursors. Actually, this method returns all the possible cursors for my data. For example, if I'm having some stream with, I don't know, the numbers 1 until 5, and I'm focused on 3, I have a StreamZipper, the focus is 3, previous lefts are 1 and 2, and the next are 4 and 5. So the method positions will return me a cursor pointing to this, to the current zipper. And one to the left, there will be the zipper, meaning a cursor pointing at 2. And if you go one left, you will have a zipper pointing at 1. If you go next, you will have a zipper pointing at 4. And if you do next, you will have a zipper pointing at 5. Now, this may look like a very, very, very slow method. It should evaluate everything, every possibility. And that's why we've used streams, because actually we can do it without evaluating anything. If you try to do a zipper for list, and having everything like a list, when you call this method, it will just evaluate everything. With a large list, it will be some out of memory or something like that. So we usually work with streams over lazy data structures. Okay, and take a look at the similarity to the regular flatten method. A flatten method, which in a regular list or a regular traversable, you just take a list of lists and just compact it into a single list. It's the basic for a flat map. And here we have the opposite, the co-flatten. Actually, this is how it should be called, co-flatten. I just enhance my data structure to represent all the possible cursors. Okay, so the implementation. Now, the implementation will be very easy if we are using fold. Take a look at the implementation. I need to create a new StreamZipper. The focus will be this, okay? The current zipper is the focus of the zipper of zippers. And to the left, we'll have all the zippers generated by the previous function. Remember, the previous function will return the previous zipper, an option of previous zipper. So we can just do unfold on the left, on the previous function, and if we'll get a none, we'll stop. This is how our unfold on stream works. We just do unfold using the previous function, but what is the result? The result is the zipper previous to me. So we'll duplicate it. It will be the seed for the next previous one, and it will be also the result. Okay, so this looks very nice. You see the left, the right, and here I'm using the fact that the left side is a reverse stream. It's a stream that the first element is the previous to me and not the start of the actual stream for the zipper. Okay, and this is very nice. This will evaluate in a constant time and will be very, very nice. And here I am having the positions method. Now, instead of I will talk about comonads. Now, regular monads, I hope you are all familiar with. It's the flat map, basically, flat map with some pure function, some constructor function. And the opposite, the dual of monad, is a comonad. A comonad provides two methods. It's an abstraction, it's a type class, and I'll not go over in this session about a general usage of comonads or something like that, but we'll talk about it in the context of zippers. So, comonad, we're having two functions. First is the extract. From my context, my type, let's say it's a zipper. A zipper actually provides a comonad instance. If I'm having some zipper, I can extract a single element. Always. Remember, in regular monad, we have the pure function, or the return function, sometimes it is called, which takes an element and returns an f of a. Here we take an f of a and return an element. You see? And in our zipper, what will be the element? The focus. Okay, remember, a zipper is always a non-empty collection, and this method always exists. There's always some focus for the cursor. And the other method is the opposite, the dual of flat map. Given some zipper, in our example, of A, and we have a function from zipper of A to some B, some value, we can provide a zipper of B. Now, you can try to do it with regular collections, like list or stream. You will not have these two methods. You cannot implement them in a sane way. But for zipper, actually, we can implement, and the co-flat map is implemented actually quite nicely. Here, the extract will be the focus, and the co-flat map is just taking the positions and mapping over them with f. I'm taking all the possible cursors and invoke f over all of them, getting from each zipper a value. Remember, I'm in the context of zippers, and for each zipper I'm having the value, so we'll just get a regular StreamZipper of the results. So, we've built all of this. Now, back to our scenario. Let's solve the sandwich people annotation, marking as Boolean, as true, each one that the previous age is less than his age, and the next one is an age greater than the element. Okay, so let's start with the business logic. This is the method, is sandwich. You see, very, very simple, easy to test, pure method. I'm having the age, the previous age, the next age, checking whether the age is greater than and lesser than previous and next age, respectively. Okay, now let's try to use the zipper. Okay, so given a zipper, and here we are focusing on a specific person. Remember, a zipper is a data structure, which direction, and the focus. I'm focusing on some person, and I want to check, I want to return the true or false. So here it is. I match the zipper, and some complex pattern match. I don't know, I like it. Some people don't like this pattern matching, which is that complex. I think it's very nice, and it's a matter of taste. You can use it with a regular extraction or however you want it. But I'm matching over here. What does this part do? The first part. Remember, every pattern match is composed of two operations: the check, whether this matches our input, and the extraction. So what I'm matching here, I'm matching whether the left, this is the left part, is non-empty. There's at least a single previous person, at least. Maybe many previous persons in that list, in the stream, I'm sorry. But there must be at least one. If the left is nil, is an empty stream, then go to the other case. And I'm only extracting the previous age. That's what I need for checking whether my age is greater than the previous age. Now, for the current, the focus person, I need the age for checking, and I will also need the person itself. Later we'll see how to get rid of it. And for the right side, I also need to check that they are not empty, that there is actually a next person. So here I'm checking it. The check is whether the stream to the right is non-empty, and the extraction is give me the next age. And now I invoke the is sandwich. Only if my age is greater than the previous age and less than the next age, I want to return the person and true. See? And here, what with that case? I need to return the person and false. Wait a second. Actually, I need to return the person itself. It's not that hard to write. It's zipper.focus, but still it looks something not that nice. It's okay to write it that way, but I think that this method should only return true or false. Okay? Sounds much nicer. That this method should only return true or false. But if that method, mark sandwich, will return a true or false, I will have a problem. Let's go back to the co-flat map. Here. Oh, sorry. Here. Let's say that this function, you see, my function gets a StreamZipper of person, and I will return true or false, a Boolean. What will I get? Only a stream of Booleans. Now I can, of course, zip it. Nothing to do with zipper. Zip it with the original stream. But I want something nicer. Okay? So there are a couple of methods that I usually introduce. They are not in the standard library. I introduce them using implicits, which are related to map, flat map, and co-flat map. For example, let's take a look at flat map. We are all familiar with flat map. Now, both map, flat map, and co-flat map forgets about the original value. A flat map is take an element of type A and return a context, let's say list, a list of B. And then you get a flattened list of Bs. But what if I wanted to maintain also the original A? I want to get, at the end, a list of tuples of A and B, the original value and the generated value by our flat map function. You can't have it. It's lost in the translation. And you need to work some hard-coded, take the value and then map it and use some magic. But I prefer to just introduce a new function. But like this is the co-flat map. I will get to it in a second. I just want to show you the flat map. Here it is, the first code section. I'm using some implicit class like rich list. Here I'm only enriching the list type. Yes, I know I should use the can build from to enrich any general traversable. For simplicity, I used only the list type. And I'm adding the flat map width, which is a very convenient function. You see, flat map width, I'm taking the regular function from A to list of Bs, but take a look at the result type. It's a list of tuples of A and Bs. Okay? This is the B generated by that method, and this A is the A that I started with. So I'm not forgetting anything here. And the implementation, very short. I do a flat map, and then I invoke the A and map each B to the tuple A and B. Okay? Very nice. Here is an example of usage. It's actually from a real project, actually in Java, God forbids. And I used something like the Scala libraries there, and actually with flat map width, something like that. I'm having apps, and I'm having servers, and the server can contain a list of applications, and I'm having some servers here, list of servers, and I want to get all the applications with their server, a tuples, list of tuples. So it's very nice when I use flat map width, and just take the apps, and it will automatically tuple it with the original value. Very nice. You can do it for map, for flat map, and I'm going back a slide with co-flat map. We have the original flat map, co-flat map, I'm sorry, and now I'm having co-flat map width. You see the result is a StreamZipper of tuples, the original type and the new value. And now just co-flat map, and I always use the focus from the previous zipper. And now, that's it. So my mark sandwich now is very nice. You see, I don't need to extract here the person. This person, I don't need to extract it. I just to return a true. And here I'm returning a false. And now the solution to what we started from is people with annotation. You see, I'm taking the people. This is a stream. You cannot create a zipper out of a stream. The stream may be empty. So a from zip stream will just check for an empty stream and return an option. If the stream is empty, then return an empty stream. Otherwise, co-flat map width mark sandwich and turn it back to stream. This will evaluate the left side. Yes, nothing to do about it, but we're having the solution. And this is what I wanted to say about zippers. Let's move on. We don't have much time to difference list. Just before, regarding comonads. If a regular monad allows me to extend for each element in my list, get a new list, and then concatenate everything, a regular monad is based on a flat map, and the flat map only works with a single element, A, from A to list of B. I'm working with an element without the context. A comonad starts with an element with its context, a StreamZipper of A, it's a focus and direction and the surroundings, and then return a value. So actually, it turns out that every directed non-empty container provides a comonad. This is very interesting, can be proven, but not going into it right now. Let's talk about TreeZipper quickly. When TreeZippers are more complicated, using regular styles for working from some node to with its surroundings is very cumbersome, and zippers are very great with trees. Well, I'm not going to show all the code here. For example, type inference on an AST is classic example for working with TreeZipper. And a TreeZipper, again, a focus. This is a simplified TreeZipper using a regular tree and not a forest. Okay? Left is a stream of trees, right is a stream of trees, and the parent an optional tree. And then we can have unfold for tree. Okay, I want to talk about difference lists, so I'll just skip the gritty details and you can check them later online, and I'll provide the presentation. Positions is a little bit more complicated, but as you can see, it's still using unfold for streams, unfold for trees, so based on the same ideas. Sorry. And now we are going to talk about difference lists. So the scenario here will be the writer monad. A writer monad is called the logging monad. I don't like this name. Regular classical logging throughout the application is not supposed to be in memory, and it will cause very, very much trouble using with the writer monad. Use it with I/O or something like that. I like the writer monad to be used for some algorithm writings. For example, here it is, the Newton-Raphson algorithm. Without writer monad, without anything, find square root, and then you guess, and if I'm close enough, I return the result, and otherwise recurse. Okay, and I get some value, the square root of 2. Now, let's say that I want to trace it, to see how it behaves during the iterations. So using the writer monad, as you can see here, I'm using the writer, I'm accumulating a list of doubles, the path. As you can see at the end result, I've started with 1, 1.5, 1.4, 1, 6, 6, 6, 6, 1, 4, 1, 4, blah, blah, blah. Okay, I see the tracing. It's very nice. Now, what's good about the writer monad is that it's typed. It's not logging, it's just lines of strings. You can actually aggregate strings also, but I can aggregate actual types and then print them in some graph and use them, discard them, do with them whatever I want. And the writer monad, the flat map, you see it's a for comprehension, the flat map here will just concatenate, append the values of the list of doubles generated by each generator in the for expression. Okay, so it's actually very nice. It takes care for the appending to the scratchpad for the logging values. However, it uses list appending. Okay? The writer monads works with any semigroup type that has an append to A's. I can create a single A, combine them, merge them, append them to a single A. If I'm having two lists, ++ will combine them to a single list. But what's wrong with ++? Okay? ++ is okay if it's right associative. Because ++ will iterate over the left side. Okay? So if I'm using right associatives ++s, then I get a nice result. Here is a benchmarking. You see, I'm having here a list of lists, and I'm using fold to append them. This is left associative appends. You see the accumulator is always appended to. Okay, this works in my computer something like 8 seconds. Now, if I just change it, and the order will be, of course, not that good, but it's, you see, I'm using right associative appends, I'm getting around 10 milliseconds. This is a huge performance difference, quadratic versus linear. So, the problem is the writer monad will work with left associative list appends. Okay, this is a problem. Now, when you have recursive concatenation, okay, you will have a problem. You will have a problem. You will get left associative appends. The writer monads, if you want, for example, build a string representation from trees, binary trees, or forests, or something like that. And also, a very nice example, if you're using graph X from Spark, there's something like send message to neighbors, and in some cases, it's not recommended, but you need to create a list of combined lists or arrays of messages that arrives at a node, and then quadratic complexity. Very, very bad. DLists to the rescue. Now, DLists stand for difference list, and the name is all incorrect. It came from Prolog. The meaning there is it's a completely different data structure, maintaining the difference between lists. It has nothing to do with difference lists in the original description in Prolog. But in functional programming, they are a very useful data structure, providing a complexity, constant complexity for appending a single element to your list, to your stream, or just concatenating DLists. It's O of 1. How can that be? Well, the naive representation, it's not the actual representation of DList, the naive representation is a function from list to list. What? It's not, where are the elements? No, it's a function from list to list. And let's take a look at from list. How do I create a DList from a list? So provided some list by name, okay, I'm creating a DList with the following function. Give me a list, some other list, B's, okay, and I will append them to the original list. You see, actually this signature reads like, give me some list, and I will return you my list concatenated with the one list that you gave me. So if you want to create a list from a DList, you just invoke f and provide the empty list. And then you get your list. So why is that encoding? This is the encoding because actually, if my DList is a function and I want to concatenate or append an element, I'm just creating another DList and compose those functions. Now, function composition is constant time. It's very fast. So actually, we are building, if we are trying to append a lot of DLists, we're just creating a chain of composed functions, one on top of the other, and that will be our final DList. And then I will just provide the empty list and get the full list from all of the chain. Now, there's a problem here. A long chain of composed functions will actually lead us to SOE, to Stack Overflow exception. By the way, someone asked me about, what about stream? Stream are lazy. Append is a constant time also because of laziness, so why don't you work with streams? Actually, if you try to work with streams, with appending, a lot of appending, you will get Stack Overflow error. Because, like this, you'll have a long chain of methods and you'll get out of stack. So, the stack problem. It turns out that there's a very old pattern, data structure to work with stack problems, long chains of compositions, called Trampoline, a trampoline. And a trampoline can trade stack space into heap space. Okay, it will be a little bit more slow, a little bit slower, but you'll get the guarantee that you will not have Stack Overflow exceptions. Let's take a quick review over trampolines. So here is a method. It looks like a tail recursion, but it's not. It's not a tail recursion. This will throw Stack Overflow exception, and it's hard to see why. The reason is that this is not an object, it's a class. And Scala compiler will do tail call optimization only for statically bounded methods. Private, static, final methods, and this method is can be overridden by someone inheriting from show1, and then you cannot do tail call elimination. So, tail call optimization, I'm sorry. So this will not work. If you try to put the annotation, of course, it will tell you that it will not work. So, trampoline to the rescue. The trampoline is a data type. This is not the full one, it's a simple one, saying that a trampoline can be either a value, done, something that we get, or a next step, a function 0. You see? A next step. And my eval function is a tail recursion, which means it's constant stack. And if it's done, return the value. Otherwise, just call eval on the next step. And here I can turn, actually, my example into tail recursion 1. Okay? You see? Now, it will work. Using trampoline, a little bit of code there, and that's nice. That's very nice, but it will be like this. But that's not all. Because what if I want to do some operation on the output? Here, I want to invoke recursively add, but append 1 to it. It will not work because add returns a trampoline. It's not an int. You cannot +1 it. And it looks like a functor. Why don't you use a map and then .map and provide the +1 inside? Okay, let's try to do it. Looks like a functor. Yes, here it is. The map, if it's done, just invoke the f on the value. Otherwise, invoke the next step and then map with f. But the problem is, this is not tail recursion. You see, it's a recursion, map and map, but not a tail recursion. And apparently, you cannot write it like this in a tail recursion way. You cannot avoid the Stack Overflow here. Not by only using done and more. I've tried it. I've tried it very hard. Cannot do it. There's no way. Okay? Even without flat map. With flat map, of course, you cannot do it. But even with map, you cannot do it. You cannot. Try it. So, actually, the solution here, and I will not go into all of the implementation detail, is to add another type to the hierarchy called flat map. Meaning, a sub-expression to compute, and then the next step. Okay, and I need to encode it in the hierarchy, and then with a lot of code, I can write it in a tail recursive way and build right associative chains on the heap and not on the stack. And actually, after talking about Trampoline, the signature for a difference list is like this. Give me a list to append to my own evaluated list. I will give you a trampoline, meaning I will do all the chaining over the heap and not over the stack. And you will be stack safe. You will not get a stack overflow for any apparent reason. And this will be great. This will be great. And DLists are very useful. With the writer monad, they provide the append, the plus plus, so you can use the writer monad and use a DList instead of list or stream or something like that. You can use it with tree traversal constructing some huge string from a tree. You can use it, maybe I haven't still used it with GraphX. There are some problems there regarding serialization, but it can be solved, and then I think it will make an important performance improvement. So there are use cases for DLists. Okay? By the way, if you have a DList, reverting to a list is a very costly operation. You need to traverse everything. And if you want to go back and forth from a DList, go to a list, take something, go back to a DList, append some more, and then take it and take some elements. So it's very costly. So there's a paper, very nice work, called Reflection Without Remorse that can show how to do it in an efficient way using type-aligned sequences. There are already some third parties, some experiments using this notion and to create a DList with good asymptotic behavior, good complexity for reflection, for taking the list, taking values out of it, and then just continue with the DList. The constants for performance there are not so good, okay, but worth a look, worth a try. It's not yet in standard third-party general use libraries, but you can try it. And that's it, I think. We have covered zippers, okay? Remember the data structures with direction and with a focus on a specific elements. You can have zippers for directed graphs, for a lot of types. For tuples, you can have zippers. Okay? Can be very nice. No, not tuples, I'm sorry. For streams, for trees, for graphs, for directed containers. We've talked about folds and unfolds, how to check if your fold is good, what's an unfold, the usefulness of unfolds. We've talked about the positions, the co-flat map. Okay, that every directed, non-empty every directed, non-empty data structure will have. Flat map widths and co-flat map widths, useful functions for just carrying on the original value with us. Co-Monads, writer monad, DLists, and trampolines, and I hope you enjoyed it. And if you have any questions now, I will answer. The question was regarding my test for folds, and I said that fold left was not good enough. It's not actually true. Fold left is good enough. It just doesn't adhere to my rule. Okay, I said the rule is an intuitive one, and it's not always correct. Because if I need to feed the constructors for list, okay, I have the nil and the plus column. The plus column takes first element. First is the element, and the second parameter is the tail. Okay? But if I'm doing a fold left, the first one is the accumulator, and the second one is the element. So I need to flip it. Okay? If I flip it, I will get everything okay. But the fold right is actually, you just put the constructors and get the result. So it's not a question of which is better, fold left or fold right, but my intuition, it's not mine actually, but the intuition goes for fold right. I've said it's not mathematically proven, it's not always correct, but it's an intuition. Okay? Both fold right and fold left you can achieve everything with it. Yes? Have some more questions? Well, I'd like to thank you all. I hope you will learn something and got something out of the talk. Thank you.